Alright, today's little rambling is for my students. Yes, you heard it correctly. If ever you thought I sound a bit like a physics teacher in my ramblings, a little bit techie, a little bit nerdy, that's because I'm a physics teacher. That's right. Today is specifically for my students. Every year in year 10, second year of GCSE, we come upon the electronics topic, which I don't always find massively interesting. Certainly not the way that it's laid out in the course book. However, when it comes to practical applications of the stuff that we learn, there is nothing better than electronic Nerf blasters. So, with all the electronic flywheel-based blasters that I upgrade, it's based on a very simple principle. You want to get more power out of your motors, or you want to put more power into your motors so that they spin faster and they dump more energy into the, in my case, rival balls, fire faster and also faster rate of fire. So you want more power. So let's quickly just recap from our electricity topic how you work out power. Power is a product of voltage and current. Okay. Now, to increase either of these two, you want to increase power, you've got to increase either one or both of these two. Now, you can increase the voltage by swapping out your stock batteries for one of these, for a LiPo. The stock battery on the Hera, go. Okay, now this looks pretty ugly, it's a bit of a hodgepodge. Any purists will have spotted that yes, there is a mixture of C-type and AA batteries, but this setup was only ever going to be for testing with me. I was going to strip all the stock electronics out and swap it over for LiPo compatible. But again, another thing from our GCSE course is series wired cells. Okay, this is our battery, these are our cells. C cells and AA's actually have the same voltage, 1.5 volts. You'll notice that positive and negative, positive, negative, positive, negative, positive, negative. The positive of one, I don't know which way, I think it goes this way, yeah. So the positive of this one links to the negative of that one. They are daisy chained in series. And in series, the voltage adds up. Each one's 1.5, 3, 6, 9. This is a 9-volt battery pack. So first thing, you can swap it out for a LiPo battery, which runs, when it's fully charged, at about just over 12 volts, right? So you're increasing this voltage here. So increasing the voltage just by having a higher voltage output on the battery will give you more power. However, the amount of current that you get through a circuit depends on something else. So one of the other things that we learn about is Ohm's law, which is the relationship between voltage, current, and resistance. So, for example, if I have a circuit with a fixed resistance and I increase the voltage, like I just said, you get more current. So you'd get more voltage and more current together without doing anything to the resistance. More voltage, more current means more power. But if you could lower this value, then increasing this and reducing that will have a bigger effect on the current. So for example, if I took the stock battery and I could somehow reduce the resistance of the circuit in the blaster, so I'd be keeping this the same, but reducing this would go up, okay? So reducing the resistance of the circuit without doing anything at all to the battery would increase the current. So, okay, you're not changing voltage, but you are increasing current. And then you look at the power equation, you would still increase the power that would be able to run through the motors. But what you can do, and this is what we do when we upgrade blasters, is you change not only the battery, which has a higher voltage output, it has a lower internal resistance, but you also go and do all of the wiring inside the blaster. So let me show you that now. I'll show you what the wiring in the stock blaster looks like. Okay, so we can see here the stock wiring, okay? So the current from the battery has to go ultimately from the battery through these fairly skinny wires partly through this switch here, has to go through quite a small switch which has got small plates on, doesn't take a lot of current. Remember, the thicker the piece of metal the current's going through, the lower the resistance, the current can go through it more easily. So we've got thin wire here, fairly small switch. Circuit boards, some of these are for safety, so if the flywheels get jammed, they don't burn out. So you've got a little circuit here for safety, more safety circuits on the motors themselves, all of which have very thin circuit paths. The metal's very thin, and all of this has quite high resistance. Okay, so, and also actually there are safety switches up here. So all of this metal, this wire, is very thin. So what we do is very simple. We strip all of this wire out, take off all the circuit boards, take all of this wire out, leave some of it in from the trigger. I'll explain why in a second. Most of the wiring, we make it much simpler, so it doesn't go through as much circuitry. We make it thicker. This is the kind of wire. You can see the difference in gauge of this wire. Really chunky. I think this is 18 gauge it's called, but it's thick wire anyway, so thick wire. And instead of passing all the current through this switch, for this type of blaster, which is a semi-automatic flywheel blaster, there's only one route that it needs to take, and that's from the battery straight into the motors. And this is what's called a Mosfet, which is a really nice, it's like a very high-powered switching circuit. So the current doesn't need to go through this rev switch. Instead, the rev switch wires I will leave in. So these wires here, I will unpick these, and I will use them to trigger this big beefy switch, so that the current goes straight from the battery in one side here and out. I can't remember which way around it goes, but in one side and out straight to the motors, again through this thicker gauge wire. So it won't go through any of the little circuitry, it won't go through this trigger here, it will go via much thicker wires from a higher voltage, lower resistance battery straight into these motors. And the difference being the end result. But this is what it looks like with all the new wiring. There's the Mosfet board, fit inside this nice big space. Circuit boards come off the motors, directly wired in parallel with each other. And it'll turn it from a gun that fires like this to one that fires like this. Leave a comment down below and let me know if you're curious about the physics of Springer blasters, or how GCSE science can be used in any other aspect of this hobby.